Hello, and welcome. I'm so glad you're here with me tonight. In this video, we're going to explore the wonderful world of space crystals together. We'll discover 100 fascinating facts about these beautiful structures that form in the vast emptiness of space. Just relax, get comfortable, and let your mind drift as we journey through the cosmos. You don't need to stay awake for all of it. Just close your eyes whenever you feel ready, and let the gentle facts about space crystals carry you into peaceful dreams. Fact 1. Space crystals form in zero gravity. Let's begin our journey with something truly magical. Space crystals form in conditions we can barely imagine here on Earth. Up in space, there is no gravity pulling things down. Everything floats freely. When crystals grow in this environment, they develop in ways that are impossible on our planet. Without gravity tugging at them, the atoms and molecules can arrange themselves perfectly. They line up in patterns that are more precise and more beautiful than anything we can create down here. Scientists have discovered that crystals grown in space are often larger and more perfect than their Earth-grown cousins. The lack of gravity means there are no currents in the liquid where the crystals form. On Earth, warmer liquid rises and cooler liquid sinks. This creates movement that disturbs growing crystals, but in space, everything stays still and calm. The crystal can grow slowly and peacefully, atom by atom, building itself into the most ideal structure possible. These space-grown crystals are not just beautiful to look at, they teach us important things about how matter organizes itself. When left alone in the pure conditions of space, research stations orbiting our planet have grown many types of crystals, from simple salt crystals to complex protein crystals that help us understand diseases. Each one forms more perfectly than it ever could under Earth's heavy pull. The silence of space, the stillness of zero gravity, allows nature to work its magic in the most pure and undisturbed way. Fact 2. Ice crystals float among the stars out in the cold darkness between stars. Tiny ice crystals drift through space. These are not like the snowflakes that fall on winter days. These ice crystals have been floating through space for millions, or even billions of years. They are incredibly cold, far colder than anything we experience on Earth. The temperature in deep space is close to absolute zero, the coldest possible temperature in the universe. At this temperature, water freezes into ice that is harder than rock. These ice crystals catch starlight as they tumble slowly through the void. They sparkle and shine in the darkness, creating clouds of glittering ice that spread across light years of space. When you look up at the night sky, some of the twinkling you see comes from these drifting ice crystals reflecting distant starlight. They are part of what astronomers call the interstellar medium, all the gas and dust and ice that fills the space between stars. These crystals play an important role in the universe. They help new stars form by gathering together over millions of years. They carry water across space, spreading this precious substance to new worlds. Some scientists believe that ice crystals from space may have brought water to Earth billions of years ago, giving our planet the oceans that made life possible. As you drift off to sleep tonight, imagine these ancient ice crystals floating peacefully through space, patient and eternal, witnesses to the slow dance of galaxies. Fact 3. Salt crystals form on dead stars when a star dies. It can create some of the most unusual crystals in the universe. Some dead stars, called white dwarfs, are so dense and so strange that their cores may be made of crystallized carbon. This is essentially a giant diamond floating in space. But even stranger, the outer layers of these dead stars can form salt crystals. As the star cools down over billions of years, the elements in its atmosphere can crystallize. Scientists have found evidence that some white dwarfs have atmospheres where salt crystals form and fall like snow. Imagine a gentle snowfall, but instead of water ice, the flakes are made of sodium chloride, common table salt. These salt crystals fall through the thin atmosphere of the dead star, glinting in the faint light that the cooling star still emits. The idea of salt snow falling on a dead star is both beautiful and peaceful. It reminds us that, even at the end of a star's life, nature continues to create order and pattern. The universe never stops making crystals, even in the strangest places. These salt crystals on white dwarfs teach us about the chemical processes that happen in extreme conditions. They show us that the same elements that make up our bodies and our world exist throughout the universe, crystallizing and organizing themselves according to the same natural laws everywhere. As you close your eyes tonight, think about those gentle salt snowflakes drifting down on a dying star, a quiet ending to a long stellar life. Fact 4. Diamonds rain on giant planets deep inside some of the giant planets in our solar system. Conditions are so intense that diamonds form and fall like rain. On planets like Neptune and Uranus, the pressure and temperature are so extreme that carbon atoms are squeezed together into diamond crystals. These diamonds form high in the planet's atmosphere and then slowly sink down through the thick layers of gas and liquid. It's like a constant gentle rain of diamonds, falling for thousands of miles through the planet's interior. Scientists discovered this possibility by studying what happens to methane, a simple molecule made of carbon and hydrogen, under extreme pressure. When you squeeze methane hard enough and heat it up, the carbon and hydrogen separate. The carbon atoms then bond together in the tight, strong pattern that makes diamond. Inside Neptune and Uranus, this happens naturally. The diamonds that form are probably quite small at first, maybe the size of raindrops or hailstones, but as they fall deeper and deeper into the planet, they may grow larger. Some could become as big as your hand, or even bigger. Eventually, they fall so deep that even diamond cannot remain solid. The temperature and pressure become so extreme that the diamonds melt into liquid carbon, joining the strange liquid ocean that makes up the deep interior of these planets. This diamond rain has probably been falling for billions of years, ever since these planets formed. It's a slow, steady process, peaceful in its constancy, a quiet rain of the hardest crystals in nature, falling through darkness, where no eye will ever see them. Fact 5. Quartz exists in moon dust. The moon, our closest neighbor in space, has crystals hidden in its dusty surface. When astronauts brought back moon rocks and moon dust, scientists found tiny quartz crystals mixed in with other minerals. Quartz is one of the most common crystals on Earth, making up much of our sand and many of our rocks. Finding it on the moon showed us that our moon and Earth share a common history. Scientists believe the moon formed when a massive object crashed into Earth billions of years ago. The impact threw huge amounts of material into space, and this material eventually came together to form the moon. Since the moon came from Earth, it makes sense that it has some of the same minerals and crystals. The quartz crystals in moon dust are very small, often microscopic. They glitter faintly in the light of the sun, mixing with the grey dust that covers the moon's surface. These tiny crystals have been sitting on the moon for billions of years, unchanged and undisturbed except when meteorites strike the surface, or when human footprints briefly disturb the dust. The moon has no weather, no wind, no rain. The crystals there remain as they were when they formed. They are patient and eternal, waiting in the silence of the lunar surface. When you look up at the moon tonight, remember that it holds countless tiny crystals, each one a small piece of the moon's ancient history, each one connected to our own Earth through the violent birth that created both worlds. Fact 6. Carbon crystals form in nebulous in the colorful clouds of gas and dust called nebulous. Carbon crystals slowly form. Nebulous are the nurseries of stars, places where new stars are being born from the material left over from older stars. These clouds contain all the elements that make up planets and life, including carbon. Carbon is a special element that can form many different types of crystals. In the cool, dense parts of nebulous, carbon atoms come together to form tiny crystals of graphite and even tiny diamonds. These crystals are incredibly small, much smaller than a grain of sand, but there are so many of them that they affect how light passes through the nebula. They absorb some colors of light and let others through, helping to give nebulous their beautiful colors. The process of crystal formation in nebulas is gentle and slow. Atoms drift through space, occasionally bumping into each other. When conditions are right, they stick together. More atoms join them, and slowly, over thousands of years, a tiny crystal forms. These crystals then become part of the next generation of stars and planets. Some of the carbon crystals in your own body, the carbon atoms that make up your DNA and your proteins, may have once been tiny crystals floating in a nebula billions of years ago. Everything in the universe is recycled. The atoms that make up new stars and planets, and eventually life, were once parts of old stars and old planets, and before that, they drifted as crystals in ancient nebulas. As you rest tonight, imagine those tiny carbon crystals forming slowly in the colorful clouds of space, patient building blocks of future worlds. Fact 7. Magnetite crystals drift in space dust throughout space. Tiny crystals of magnetite float in the dust between stars. Magnetite is a magnetic iron oxide, the same mineral that makes natural magnets. These tiny magnetic crystals form when iron from old stars combines with oxygen and crystallizes. Each crystal is incredibly small, but each one has a magnetic field. As these crystals drift through space, their magnetic fields interact with the magnetic fields that fill the galaxy. This interaction affects how the crystals move and align themselves. Over time, magnetic crystals can line up along the invisible magnetic field lines that stretch across space. Scientists study these magnetite crystals because they help us understand the magnetic environment of space. Earth also has magnetite crystals, and some living things use them to sense direction. Birds have tiny magnetite crystals in their brains that help them navigate. Using Earth's magnetic field, the magnetite in space dust reminds us that magnetism is a fundamental force of nature, working everywhere in the universe. These drifting magnetic crystals also play a role in how new solar systems form. When clouds of dust and gas collapse to form new stars and planets, the magnetic fields carried by magnetite crystals help shape how the material falls together. They add an organizing influence to the chaos of formation. As you settle in for sleep tonight, think of these tiny magnetic crystals, each one a miniature compass, floating through space and slowly spinning in response to the invisible magnetic currents that flow through our galaxy. Fact 8. Olivine crystals color space green. Olivine is a beautiful green crystal that exists both on Earth and in space. On Earth, gem-quality olivine is called peridot, a lovely green gemstone. In space, olivine crystals form in comets, asteroids, and even in the dust clouds around young stars. When olivine is heated or exposed to light, it glows with a distinctive green color. Astronomers have detected this green glow coming from comets and from young solar systems. The green light tells them that olivine crystals are present and are being heated by nearby stars. Olivine forms when molten rock cools and crystallizes. In space, this can happen in the hot environment near a young star, or deep inside asteroids that were once hot enough to be partially molten. As these bodies cool, olivine crystallizes along with other minerals. The crystals that form in space can be quite pure and beautiful. Comets, those icy travelers that swing through the solar system, often contain olivine mixed in with their ice. When a comet approaches the sun and its ice begins to evaporate, the olivine crystals trapped in the ice are released. They catch the sunlight and glow green, creating a faint green haze around the comet. This green glow is subtle and hard to see, but instruments can detect it. The presence of olivine in comets tells us that these icy bodies contain material that was once very hot, suggesting they formed in the inner solar system and were later thrown outward. As you drift into dreams, imagine those green olivine crystals glowing softly in the tails of distant comets, adding their gentle color to the darkness of space. Fact 9. Methane ice crystals on Titan. Titan, the largest moon of Saturn, has a surface covered in crystals of methane ice. Titan is a strange and wonderful world. It has an atmosphere thicker than Earth's, and it's the only other place in the solar system besides Earth that has stable liquid on its surface. But instead of water, Titan's lakes and seas are made of liquid methane and ethane. The temperature on Titan is incredibly cold, about -280 degrees Fahrenheit. At this temperature, methane behaves the way water does on Earth. It evaporates from the lakes, forms clouds, falls as rain, and freezes into ice. The mountains and rocks on Titan are made of water ice, which is as hard as rock at those temperatures. But on top of this water ice, methane ice crystals form. When methane rain falls on Titan and then freezes, it creates a landscape dusted with methane ice crystals. These crystals are probably similar to snow crystals or frost here on Earth, but made of methane instead of water. They glitter in the dim light of the distant sun, creating a landscape that is both familiar and alien. Methane ice crystals also form in Titan's clouds, high in its thick atmosphere. These clouds are orange and hazy, giving Titan its distinctive color when viewed from space. The methane crystals in the clouds slowly grow and eventually become heavy enough to fall as rain. This rain then adds to the lakes and seas below, and the cycle continues. As you relax and prepare for sleep, picture Titan's strange beauty. Orange skies, methane rain falling slowly in the low gravity, and everywhere, tiny crystals of methane ice catching the faint light. Fact 10. Silicate crystals build rocky planets. Rocky planets like Earth and Mars are made largely of silicate crystals. Silicates are compounds of silicon and oxygen, usually combined with other elements like iron, magnesium, or calcium. These crystals form the rocks and minerals that make up the solid surface of rocky planets. When the solar system was young, it was filled with dust and gas. As this material came together to form planets, the dust particles were mostly tiny silicate crystals. These crystals stuck together, gradually building up larger and larger bodies. Over millions of years, these growing bodies heated up from the energy of countless collisions. The heat melted the rock, creating oceans of molten lava. As these lava oceans slowly cooled, new silicate crystals formed, growing in the cooling liquid. These crystals settled and arranged themselves, with denser crystals sinking toward the planet's core, and lighter crystals floating toward the surface. This process created the layered structure that rocky planets have today. The most common silicate crystal in Earth's mantle is called olivine, the same green crystal we discussed earlier. In Earth's crust, other silicate crystals like quartz and feldspar are more common. Each type of silicate crystal has its own structure and properties, and together they create the solid ground beneath our feet. The same process happened on Mars, Venus, Mercury, and the Moon. All of these worlds are built from silicate crystals that formed billions of years ago. These crystals have witnessed the entire history of our solar system. As you close your eyes tonight, rest assured that you are lying on a world built from countless crystals, each one a small piece of planetary architecture. Fact 11. Ammonia ice on cold moons in the outer solar system, where the sun's warmth barely reaches. Moons orbit the giant planets in frozen silence. Many of these moons have surfaces made partly of ammonia ice crystals. Ammonia is a compound of nitrogen and hydrogen. On Earth, it's a gas at normal temperatures, with a sharp, distinctive smell. But in the extreme cold of the outer solar system, ammonia freezes solid, forming crystals that mix with water ice. These ammonia ice crystals create landscapes that are strange and beautiful. They affect the color of the moon's surface, sometimes giving it a slightly yellow or brown tint. They also change how the ice behaves. Pure water ice is hard and brittle when frozen, but when ammonia is mixed in, the ice becomes softer and more flexible. This allows the ice to flow slowly over time, like a glacier. Some moons, like Enceladus, a small moon of Saturn, have geysers that spray water mixed with ammonia into space. This mixture freezes instantly in the cold vacuum, forming tiny ice crystals that catch the sunlight and create a glittering cloud around the moon. These crystals eventually fall back to the surface or escape into space, where they become part of Saturn's rings. The ammonia in these crystals comes from deep inside the moon, suggesting that there are hidden oceans beneath the icy surface. Scientists are very interested in these hidden oceans because they might contain life. The ammonia acts like antifreeze, keeping the water liquid even in the intense cold. As you drift towards sleep, imagine these distant frozen moons. Their surface is covered in ammonia ice crystals, and beneath them, dark oceans where strange forms of life might swim in silence. Fact 12. Calcium carbonate in meteorites. When meteorites fall to Earth from space, they sometimes contain crystals of calcium carbonate. This is the same mineral that makes up limestone, marble, and chalk here on Earth. Finding it in meteorites tells us something important. Water once flowed on the asteroid or planet where the meteorite came from. Calcium carbonate forms when calcium-rich minerals react with carbon dioxide dissolved in water. On Earth, this happens in oceans and in underground caves. Sea creatures use calcium carbonate to build their shells, and over millions of years, these shells accumulate to form thick layers of limestone. In space, calcium carbonate forms on asteroids that once had liquid water on their surface or in their interior. When scientists find calcium carbonate crystals in a meteorite, they know that liquid water was present when that meteorite was part of a larger body. Billions of years ago, these crystals are like fossils of ancient water, preserving evidence of a wetter past. The calcium carbonate crystals in meteorites are often small and delicate. They form beautiful patterns when viewed under a microscope. Tiny geometric shapes that reflect the orderly arrangement of atoms within the crystal. Each crystal is a tiny record of chemical reactions that happened long ago on a distant asteroid. Some meteorites even contain tiny spheres of calcium carbonate that formed as droplets of mineral-rich water dried up. These spheres are perfectly round, shaped by the surface tension of the water drop before it evaporated away. As you rest tonight, think of these tiny calcium carbonate crystals, messengers from the ancient past, telling us about water that flowed on asteroids when the solar system was young. Facts 13. Sulfur crystals on Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Its surface is covered with sulfur crystals in many different colors. Io's intense volcanic activity is caused by Jupiter's enormous gravity, which squeezes and stretches the moon as it orbits. This constant flexing heats Io's interior, keeping it molten and active. The volcanoes on Io erupt constantly, shooting plumes of sulfur and sulfur dioxide hundreds of miles into space. When this material falls back to the surface, it creates deposits of sulfur crystals. Sulfur can form crystals in many different colors, depending on its temperature and how it crystallizes. On Io, you can find yellow sulfur, red sulfur, orange sulfur, and even white sulfur dioxide frost. These colorful sulfur crystals give Io its distinctive appearance. Images from space probes show a world that looks like a giant pizza, with patches of yellow, red, orange, and white covering its surface. Each color represents a different type of sulfur crystal or a different volcanic deposit. The sulfur crystals on Io are constantly being covered by new volcanic eruptions, and then exposed again as the material shifts. The surface is always changing, making Io a dynamic and active world. Despite the constant volcanic activity, there is something peaceful about imagining these colorful sulfur crystals forming and reforming on Io's surface. The process has been going on for billions of years, and it will continue for billions more. As you settle in for the night, picture Io's colorful surface, its sulfur crystals glinting in the light of distant Jupiter, a world of endless change that somehow remains the same. Fact 14. Water ice crystals in Saturn's rings. Saturn's magnificent rings are made almost entirely of water ice crystals. From Earth, the rings look solid, but they are actually made of countless individual pieces of ice, ranging in size from tiny grains to house-sized boulders. Each piece is a crystal or a collection of crystals of frozen water. The ice in Saturn's rings is very pure and very clean, which is why the rings are so bright and reflective. They catch sunlight and shine brilliantly, making Saturn one of the most beautiful sights in the solar system. The ice crystals in the rings are in constant motion, orbiting Saturn at different speeds depending on their distance from the planet. When these ice crystals collide with each other, they sometimes stick together, forming larger clumps. Other times, the collisions break them apart into smaller pieces. This process has been going on since the rings formed, possibly billions of years ago. Scientists are still not completely sure where Saturn's rings came from. They might be the remains of a moon that was torn apart by Saturn's gravity, or they might be leftover material from when Saturn formed. Either way, the result is a spectacular display of countless ice crystals arranged in a thin disk around the planet. The rings are surprisingly thin, often only a few tens of feet thick, despite being hundreds of thousands of miles wide. If you could fly through Saturn's rings, you would see ice crystals of all sizes glittering around you, each one following its own orbit, each one catching and reflecting the light of the sun. As you drift towards sleep tonight, imagine yourself floating peacefully among Saturn's rings, surrounded by gently tumbling ice crystals that sparkle in the sunlight. Fact 15. Iron crystals in Earth's core deep beneath our feet, at the very center of the Earth. The planet's core is made of iron and nickel crystals. The pressure at Earth's core is so immense that despite temperatures hot enough to melt rock, the iron there is squeezed into solid crystal form. These are the largest crystals on Earth, extending for hundreds of miles. The iron crystals in Earth's core are not randomly arranged. They have aligned themselves along the north-south axis, following the planet's magnetic field. This alignment affects how earthquake waves travel through the core, allowing scientists to study these unreachable crystals indirectly. The iron crystals at Earth's core have been growing for billions of years as the planet slowly cools. As heat escapes from Earth's interior, the molten outer core gradually freezes onto the solid inner core, adding new layers of iron crystals. This process releases energy that helps drive Earth's magnetic field. Without these iron crystals deep below, Earth would not have the magnetic field that protects us from harmful radiation from space. The formation of these crystals is directly connected to the existence of life on Earth's surface. The journey of heat and material through the Earth, from the hot core to the cool surface, drives plate tectonics and volcanism. These processes recycle material and create diverse environments where life can thrive. The iron crystals at Earth's core are the still, stable foundation of all this dynamic activity. As you lie in bed tonight, remember that far below you, at the heart of the planet, enormous iron crystals rest in silence and darkness, anchoring the world and protecting it with their magnetic influence. Fact 16. Forsterite crystals around young stars. Astronomers have discovered clouds of forsterite crystals. Forsterite is a magnesium-rich form of olivine, the green crystal we mentioned earlier. These crystals form in the hot environment close to young stars, where temperatures are high enough to vaporize rock. As the vaporized rock cools, it crystallizes directly from gas to solid, forming tiny perfect crystals of forsterite. The presence of forsterite crystals around young stars tells us about the process of planet formation. These crystals are building blocks for future planets. They stick together with other dust particles, gradually forming larger and larger clumps that eventually become asteroids, comets, and planets. Our own solar system went through this stage billions of years ago, when the sun was young. The forsterite crystals that formed around the young sun eventually became part of Earth and the other rocky planets. You might have forsterite crystals in the rocks near your home. The crystals around young stars glow warmly in infrared light. Instruments on space telescopes can detect this glow and map out the distribution of crystals in the disk of dust and gas surrounding the star. These maps show us planets in the process of forming, a slow construction project that takes millions of years. The forsterite crystals are patient participants in this process, drifting slowly through space, occasionally colliding and sticking together, gradually building the framework of a new planetary system. As you close your eyes and relax, think about those tiny forsterite crystals orbiting young stars across the galaxy, each one a potential piece of a future world where new forms of life might someday evolve. Fact 17. Dryas crystals at Martian poles. Mars, our neighboring planet, has polar ice caps that contain both water ice and Dryas crystals. Dryas is frozen carbon dioxide, the same gas we breathe out with every breath. On Earth, Dryas only exists in special conditions, but on Mars, it forms naturally. Mars has a thin atmosphere made mostly of carbon dioxide. During the Martian winter, it gets cold enough at the poles for carbon dioxide to freeze out of the atmosphere and fall as dry as snow. This snow accumulates in thick layers, creating bright white polar caps. In the summer, when temperatures rise slightly, the Dryas sublimates, meaning it turns directly from solid to gas without becoming liquid. The Dryas crystals on Mars create some interesting phenomena. As the Dryas sublimes in the spring, it can cause the ground beneath to become unstable. Sometimes large chunks of Dryas sublimate rapidly, causing small explosions that throw dust and sand into the air. These create strange dark streaks and spots on the Martian surface that change with the seasons. Scientists have watched these patterns appear and disappear year after year. The process of Dryas formation and sublimation also helps drive the Martian weather. The seasonal changes in the polar ice caps cause pressure changes in the atmosphere, which create winds. These winds blow dust around the planet, sometimes creating global dust storms that obscure the entire Martian surface. Despite being a dead world with no life, Mars is still dynamic and active, largely because of the cycle of Dryas crystals forming and disappearing at the poles. As you prepare to sleep, imagine the Martian poles, silent and cold, where Dryas crystals glitter in the thin pink light of a distant sun. Fact 18. Spinel crystals in the deep mantle deep within Earth, far below the crust and even below the upper mantle. Minerals undergo transformations under extreme pressure. One of these transformations creates spinel crystals. Spinel is a hard mineral that can contain various elements like magnesium, iron, and aluminum. In the deep parts of Earth's mantle, the intense pressure forces the atoms in common minerals to rearrange themselves into the denser spinel structure. These spinel crystals exist in a realm we can never directly observe. They form at depths of hundreds of miles, where the pressure is hundreds of thousands of times greater than at Earth's surface. No drilling machine can reach these depths. Everything we know about these crystals comes from indirect evidence, like earthquake waves that travel through the deep earth and reveal its structure. Sometimes pieces of the deep mantle are brought to the surface by volcanic eruptions. These rare samples contain tiny spinel crystals that offer us a glimpse of the hidden world below. Scientists study these crystals carefully, examining their structure and composition to learn about conditions in the deep earth. The transformation of minerals into spinel and other high-pressure forms affects how heat and material move through the planet. It influences the convection currents that drive plate tectonics and cause earthquakes and volcanoes. The tiny spinel crystals in the deep mantle are part of the vast, slow-moving machinery that shapes the surface of our planet. They have been there for billions of years, slowly crystallizing and changing as the Earth evolves. As you lie still and quiet tonight, think of those spinel crystals deep in the Earth, patient and enduring, part of the slow dance of the planet's interior. Fact 19. Amino acid crystals in meteorites. One of the most exciting discoveries in the study of space crystals is finding amino acids in meteorites. Amino acids are the building blocks of proteins, and proteins are essential for all life on Earth. Finding amino acid crystals in space rocks tells us that the ingredients for life are not unique to Earth, but exist throughout the universe. When certain types of meteorites called carbonaceous chondrites are analyzed, scientists find them rich in organic compounds, including amino acids. These amino acids can crystallize under the right conditions, forming small but beautiful crystals. The amino acids in meteorites are formed by chemical reactions in space, possibly in the interiors of asteroids where liquid water once existed. The discovery of amino acids in meteorites supports the idea that life's building blocks may have been delivered to Earth from space billions of years ago. The young Earth was bombarded by asteroids and comets, and these impacts would have deposited organic compounds on the surface. These compounds could have provided the raw materials that eventually led to the origin of life. The amino acid crystals in meteorites are fragile and rare, but they carry a profound message. They tell us that we are connected to the cosmos in the most fundamental way. The same chemical processes that create crystals in asteroids also create the molecules that make up our bodies. We are, quite literally, made of stardust, made of the same atoms and molecules that form crystals in space. As you drift into dreams tonight, take comfort in this connection. You are part of the universe, made from its elements, shaped by its laws, a conscious arrangement of atoms that can wonder at its own existence. Fact 20. Troy-like crystals in iron meteorites. Iron meteorites, chunks of metal that fall to Earth from space, often contain crystals of troilite. Troilite is iron sulfide, a bronze-colored mineral that forms under conditions very different from those on Earth's surface. These crystals formed billions of years ago in the cores of large asteroids. These ancient asteroids were once big enough to melt and differentiate, with heavy metals like iron sinking to the center. In these metallic cores, troilite crystallized alongside the iron and nickel. When asteroids collide in space, they can shatter, sending fragments flying through the solar system. Some of these fragments eventually fall to Earth as iron meteorites, carrying their troilite crystals with them. The troilite crystals in iron meteorites are beautiful when polished and etched with acid. They appear as bronze-colored inclusions in the silvery metal, creating striking patterns. These patterns tell the story of how the metal cooled over millions of years. In the heart of an asteroid, the slow cooling allowed large, well-formed crystals to grow. When you hold an iron meteorite containing troilite, you are holding a piece of an ancient world that no longer exists. The parent asteroid was destroyed long ago, but its fragments survive, carrying the crystals that formed in its core. These crystals are older than Earth, older than the planets. They formed when the solar system was still young and chaotic. The troilite crystals have survived billions of years of cosmic history, weathering countless events, finally arriving here where we can study them and appreciate their beauty. As you settle down for the night, think of these ancient crystals, survivors from the dawn of the solar system, silent witnesses to eons of cosmic history. Fact 21. Xenon ice crystals on Pluto. At the edge of our solar system, on the surface of Pluto, scientists have found evidence of exotic ices that exist nowhere else. Pluto is so cold and so distant from the Sun that even gases we think of as permanent can freeze solid there. One of these gases is xenon, a heavy noble gas that remains gaseous even at very low temperatures on Earth. But on Pluto, where temperatures drop to nearly -400 degrees Fahrenheit, xenon can freeze into ice crystals. These xenon ice crystals would be found mixed with ices of nitrogen, methane, and carbon monoxide, creating a complex frozen surface unlike anywhere else. The presence of frozen xenon and other exotic ices makes Pluto's surface incredibly diverse. Different ices have different colors and different textures. They evaporate and refreeze at different rates, creating a constantly changing landscape. Some areas of Pluto's surface are covered in nitrogen ice plains that appear to flow like glaciers. Other areas have methane ice mountains that rise miles high. Mixed throughout are patches of other frozen compounds, including possibly xenon ice in the coldest regions. The New Horizons spacecraft, which flew past Pluto in 2015, revealed a world far more complex and beautiful than anyone expected. The images showed a place with varied terrain, active geology, and an atmosphere that snows. The different ice crystals on Pluto's surface interact with sunlight and with Pluto's thin atmosphere, creating subtle colors and patterns. As you relax tonight, imagine Pluto, distant and cold, its surface covered in exotic ice crystals that glitter in the faint light of the sun, a frozen world at the edge of the solar system. Fact 22. Silicon carbide from ancient stars. Some meteorites contain tiny crystals of silicon carbide that are older than the sun. These microscopic crystals, sometimes called stardust grains, formed in the atmospheres of stars that died before our solar system was born. When a star reaches the end of its life, it swells up and sheds its outer layers into space. In these expanding clouds of gas, silicon and carbon atoms come together to form silicon carbide crystals. These crystals are incredibly hard and resistant to heat and chemical change, so they survive the death of their parent star. They drift through space, eventually becoming part of the cloud of gas and dust that formed our solar system. When the solar system formed, these ancient crystals were incorporated into asteroids and comets. Eventually, some of these asteroids reached Earth as meteorites, bringing the ancient silicon carbide crystals with them. Scientists can identify these Prazola grains by their unusual isotopic compositions. The isotopes of elements in these crystals are different from the isotopes found in solar system material, proving they formed in a different star. By studying these crystals, scientists can learn about the stars that existed before the sun. Each crystal is a time capsule from the ancient past, carrying information about stellar processes that happened billions of years ago. Some of these silicon carbide crystals are more than 7 billion years old, formed when the universe was less than half its current age. They have traveled across the galaxy, survived the formation of the solar system, and arrived here where we can study them. As you close your eyes tonight, think of these ancient crystals, older than the sun itself, witnesses to the death of distant stars, now resting quietly in museums and laboratories where scientists marvel at their age and their journey. Fact 23. Graphite crystals in meteorites. Meteorites sometimes contain crystals of graphite, the same material that makes up pencil lead. Graphite is pure carbon, just like diamond, but arranged in a different crystal structure. In graphite, the carbon atoms form flat sheets that slide easily over each other, making graphite soft and slippery. This is why it works so well in pencils and as a lubricant. In space, graphite crystals form in several ways. They can crystallize from carbon-rich gas in the atmospheres of stars, or they can form when carbon-containing minerals are heated and altered. Some meteorites contain graphite that formed billions of years ago, when the solar system was still young. These ancient graphite crystals tell us about conditions in the early solar system. The graphite in meteorites is often found as small shiny flakes mixed in with other minerals. When light hits these flakes, they sparkle and reflect, creating beautiful patterns in the rock. Scientists study meteoritic graphite because it can contain trapped gases from the early solar system. These gases are like tiny bubbles of ancient atmosphere, preserved inside the crystal for billions of years. By analyzing these trapped gases, scientists learn about the composition of the solar nebula, the cloud of gas and dust from which the planets formed. Graphite is also interesting because it represents one possible form of carbon in space. Carbon is a versatile element that can form many different types of crystals and compounds. In some environments, it becomes diamond. In others, it becomes graphite. In still others, it forms complex organic molecules. The graphite crystals in meteorites remind us of carbon's flexibility and importance in the chemistry of the universe. As you relax and let your mind drift, imagine those dark, shiny graphite flakes in ancient rocks, each one holding tiny samples of the air that filled the young solar system. Fact 24. Halite crystals from asteroid impacts. Deep inside some asteroids, scientists have found crystals of halite, which is common table salt. These salt crystals formed in pockets of salty water that existed inside asteroids billions of years ago. The presence of salt crystals tells us that liquid water once flowed through the interiors of these asteroids, creating briny pools where salt could crystallize. The halite crystals in meteorites are remarkable because they sometimes contain tiny pockets of liquid water trapped inside. This water has been sealed inside the crystal for billions of years, preserved perfectly. It's some of the oldest water in the solar system, and it tells us about the salty oceans that may have existed inside early asteroids. When asteroids first formed, many of them contained ice mixed in with rock and metal. As the asteroids grew larger, radioactive elements in their interiors released heat. This heat melted the ice, creating liquid water inside the asteroid. This water dissolved minerals from the surrounding rock, becoming salty. When conditions were right, the dissolved salt crystallized, forming halite crystals. The halite crystals in meteorites are usually small and cubic. The characteristic shape of salt crystals, they are clear or slightly cloudy, and when scientists examine them under a microscope, they can see the tiny fluid inclusions trapped inside. These inclusions are incredibly precious to science because they represent samples of the very first oceans in the solar system. Oceans that existed not on planets, but inside asteroids. As you prepare to sleep, think of those tiny salt crystals, each one containing a microscopic drop of ancient salty water, a reminder that water and the conditions for life may be more common in the universe than we once thought. Fact 25. Corundum crystals in space. Dust corundum is one of the hardest minerals in nature. On Earth, gem-quality corundum is known as ruby or sapphire, depending on its color. In space, corundum crystals form in the atmospheres of certain types of stars and in the dust clouds around them. These tiny crystals are incredibly hard and resistant to change, so they survive the journey through space and can be found in meteorites and in dust collected from comets. Corundum is aluminum oxide, a simple compound of aluminum and oxygen. It forms at high temperatures, which is why it crystallizes near stars. The crystals that form in stellar atmospheres are usually very small, much smaller than a grain of sand, but despite their tiny size, they are remarkably perfect. The high temperatures and slow cooling in space allow the atoms to arrange themselves in the most ideal crystal structure. When corundum crystals are found in meteorites, they appear as small, hard grains that resist weathering and chemical change. Even after billions of years, these crystals remain unchanged. Scientists can study them to learn about the stars where they formed. Different types of stars produce corundum with different characteristics, so each crystal carries information about its stellar birthplace. The presence of corundum in space dust shows us that even the most precious gemstones on Earth have cosmic origins. The rubies and sapphires we treasure are made of the same material as these tiny space crystals. They differ mainly in size and in the impurities that give them color. A ruby gets its red color from traces of chromium in the corundum crystal structure. A sapphire gets its blue color from traces of iron and titanium. As you drift towards sleep, imagine those tiny corundum crystals forming in the hot atmosphere of a distant star, each one a potential ruby or sapphire, drifting through space on journeys that last millions of years. Fact 26. Westite crystals in lunar soil on the Moon. Scientists have found crystals of westite, a rare iron oxide mineral. Westite forms only under conditions where oxygen is limited, which makes it unusual on Earth but possible on the Moon. The Moon's surface has been bombarded by meteorites for billions of years. These impacts create intense heat and pressure, causing the minerals in the lunar soil to melt and recombine. As the molten material cools, new minerals crystallize, including westite. The westite crystals in lunar soil are tiny and often mixed with other minerals. They formed in the aftermath of meteorite impacts, in the brief moments when rock melted and then rapidly cooled. These crystals tell us about the violent history of the Moon's surface. Every square inch of the Moon has been hit by meteorites countless times, and each impact created a small amount of heat that altered the soil. over billions of years. This process has turned the moon's surface into a complex mixture of many different minerals and crystals. The lunar soil is not like soil on Earth, which is created by weathering and biological processes. Instead, it's a powder of crushed and melted rock, constantly churned by impacts. The westite crystals are part of this strange soil, along with fragments of many other minerals. When astronauts walked on the moon, they noticed that the lunar dust stuck to everything. It was abrasive and difficult to remove. This dust contains countless tiny crystals, including westite, each one a small piece of the moon's impact history. As you rest tonight, think of the moon's surface. Its ancient soil filled with tiny crystals formed in the heat of countless impacts. A quiet record of violence now long past. Fact 27. Enstatite crystals in meteorites. Enstatite is a magnesium silicate mineral that forms crystals in certain types of meteorites. These meteorites, called enstatite chondrites, are unusual because they formed in an oxygen-poor environment. Most meteorites contain minerals that crystallized in the presence of oxygen, but enstatite chondrites tell us about a different region of the early solar system, one where oxygen was scarce. The enstatite crystals in these meteorites are pale green or gray. They have a distinctive appearance that makes them easy to identify. The crystals formed when the solar nebula was still hot and dusty, before planets existed. Small particles of enstatite condensed directly from the gas, forming tiny crystals that drifted through space. Over time, these crystals stuck together with other dust particles, gradually building up into larger bodies. Some enstatite chondrites are very similar in composition to Earth. In fact, Earth may have formed mostly from material like that found in enstatite chondrites. This suggests that Earth formed in a region of the solar nebula where oxygen was relatively scarce. At least in the earlier stages, the enstatite crystals in these meteorites may be very similar to the crystals that first came together to build our planet. When scientists examine enstatite crystals under a microscope, they see beautiful, well-formed shapes. The crystals have clean edges and smooth faces, showing that they grew slowly and carefully in the hot gas of the solar nebula. They are messengers from a time before Earth existed, carrying information about the conditions that led to our planet's formation. As you settle into sleep, imagine those enstatite crystals forming in the hot, dusty cloud around the young sun, slowly coming together over millions of years to build the materials that would eventually become Earth. Fact 28. Chromite crystals in lunar rocks. When astronauts brought rocks back from the moon, scientists found crystals of chromite mixed in with other minerals. Chromite is an iron chromium oxide, a dark metallic mineral that is the main ore of chromium on Earth. Finding it on the moon tells us that the moon's interior once had molten rock similar to Earth's. Chromite crystals form when molten rock cools and crystallizes. They are one of the first minerals to crystallize from cooling lava, because they form at high temperatures. As the lava cools, chromite crystals grow and then settle to the bottom of the magma chamber because they are dense. Over time, this process can create layers rich in chromite. On the moon, chromite crystals formed billions of years ago when the moon's interior was hot and molten. As the moon cooled, the molten rock crystallized, creating the moon's crust and mantle. Some of this crystallized rock was later brought to the surface by volcanic eruptions, or by meteorite impacts that dug deep into the moon. The chromite crystals in lunar rocks are small and dark, appearing as shiny black or brown grains when light reflects off them. They are mixed in with lighter colored minerals, creating a speckled appearance. These crystals have remained unchanged for billions of years because the moon has no weather, no erosion, and no geological activity. They are preserved exactly as they formed. By studying chromite and other minerals in lunar rocks, scientists learn about the moon's history. They can determine when the rocks formed, how hot the moon's interior was, and how the moon's composition compares to Earth's. Each crystal is a small piece of evidence in the larger story of how the moon and Earth evolved together. As you close your eyes, Picture those dark chromite crystals in moon rocks, witnesses to the moon's ancient volcanic past, now silent and still in the airless lunar environment. Fact 29. Calcite crystals in carbonaceous chondrites. Carbonaceous chondrites are a special type of meteorite that contains water-bearing minerals and organic compounds. Some of these meteorites also contain crystals of calcite, a form of calcium carbonate. Calcite is the mineral that makes up limestone and marble on Earth. Finding it in meteorites tells us that liquid water existed on the parent asteroid. Because calcite forms when calcium-rich minerals react with water containing dissolved carbon dioxide. The calcite crystals in carbonaceous chondrites are usually small and delicate. They formed in veins and pockets where water once flowed through the asteroid's interior. This water was probably salty and rich in dissolved minerals. As the water evaporated or cooled, the dissolved minerals crystallized, creating calcite and other crystals. These calcite crystals are important because they provide direct evidence of liquid water. In the early solar system, liquid water is essential for life as we know it. So finding evidence of water on asteroids raises the possibility that simple chemical processes leading toward life could have occurred there. The water on these asteroids existed billions of years ago, when the solar system was young and chaotic. The calcite crystals formed during this ancient time have been preserved ever since, protected inside the asteroid until a collision sent fragments flying toward Earth. When scientists examine calcite crystals from meteorites, they often find complex patterns and shapes. The crystals sometimes show evidence of having dissolved and recrystallized multiple times, suggesting that water flowed through the asteroid on several occasions. Each layer in the crystal is like a page in a history book, recording events that happened billions of years ago. As you relax and let sleep approach, think of those calcite crystals forming in the dark interior of an ancient asteroid, growing slowly in water that flowed through cracks and channels. Water that has long since vanished, but left these crystals as evidence of its existence. Fact 30. Comosite crystals in iron meteorites. Iron meteorites contain beautiful crystals of comosite, an iron-nickel alloy. Comosite crystals form very slowly as molten metal cools in the core of an asteroid. Because space is a good insulator and asteroids cool very slowly, the metal in their cores can take millions of years to solidify. This extremely slow cooling allows very large crystals to form, creating beautiful patterns. When an iron meteorite is cut, polished, and etched with acid, the comosite crystals become visible as a pattern of intersecting bands, called a Widmansten pattern. This pattern is unique to iron meteorites and cannot be reproduced artificially. Because we cannot cool metal slowly enough on Earth, the pattern proves that the metal cooled over millions of years in space. The comosite crystals in iron meteorites are intergrown with another nickel-iron mineral, called tannite. Together, these two minerals create the distinctive striped pattern. The width of the bands tells us how fast the metal cooled. Wider bands mean slower cooling, which happens in larger asteroids that retain heat longer. By measuring the band width, scientists can estimate the size of the asteroid where the meteorite came from. These iron-nickel crystals are remnants of the cores of destroyed asteroids. Long ago, when the solar system was young, there were many large asteroids, some big enough to have melted and differentiated like planets. In these asteroids, heavy metals like iron sank to the center, forming a metallic core. Over time, collisions between asteroids shattered some of them, exposing their cores. Fragments of these cores eventually fell to Earth as iron meteorites. The comosite crystals they contain are the largest crystals we can hold in our hands, some individual crystals extending 4 inches, or even feet. As you drift into sleep, imagine those comosite crystals growing atom by atom in the cooling core of an asteroid, taking millions of years to form their beautiful patterns. Patterns we can now admire billions of years later. Fact 31. Perovskite crystals in the deep Earth. Deep in Earth's mantle, at depths greater than 400 miles, Common minerals transform into denser forms to withstand the enormous pressure. One of these high-pressure minerals is perovskite, which is thought to be the most abundant mineral in Earth's mantle, even though we can rarely see it at the surface. Perovskite has a special crystal structure that can accommodate many different elements, making it stable under extreme conditions. The perovskite crystals deep in Earth's mantle are part of the slow convection currents that drive plate tectonics. Hot perovskite-rich rock rises from near the core, while cooler rock sinks back down. This movement transfers heat from Earth's interior to the surface and causes the continents to drift and the ocean floor to spread. The crystals themselves are very small, but there are countless numbers of them making up the vast majority of Earth's volume. Sometimes volcanic eruptions bring up rocks from deep in the mantle. These rocks contain minerals that were once perovskite, but transformed back into other minerals. As the pressure decreased during their journey to the surface, scientists can see evidence of the original perovskite structure in these transformed minerals, giving us clues about conditions deep below. In recent years, scientists have also found natural perovskite crystals in certain rare meteorites. These formed under conditions of extreme shock when asteroids collided at high speeds. The impact created pressures and temperatures high enough to form perovskite, which was then preserved in the meteorite. These samples are precious because they are the only natural perovskite crystals we can study directly. As you rest tonight, remember that beneath you, far deeper than anyone can dig, the planet is made mostly of perovskite crystals, slowly flowing and moving, carrying heat from the core to the surface. Part of the great engine that keeps our planet geologically alive. Fact 32. Escalate crystals in moon rocks. Escalate is a rare chromium oxide mineral that was first discovered in lunar samples brought back by the Apollo astronauts. Before the moon missions, escalate had only been synthesized artificially in laboratories. Finding it naturally occurring on the moon was a surprise. The mineral was named after Pentti Eskala, a Finnish geologist, and its presence on the moon tells us about the reducing conditions that existed when lunar rocks formed. Escalate crystals are small and dark green. They formed in the moon's interior billions of years ago, when molten rock cooled and crystallized. The moon's interior had very little oxygen available, creating reducing conditions where chromium could form escalate, instead of the more common chromite. These unusual conditions are part of what makes the moon's geology different from Earth's. The discovery of escalate in moon rocks helped scientists understand that the moon formed under different chemical conditions than Earth. This was one of many clues that led to the current theory of the moon's formation, that a Mars-sized object crashed into Earth early in its history, and the moon formed from the debris of that collision. The material that became the moon was heated to extreme temperatures and lost many of its volatile elements, creating the reducing conditions where escalate could form. The escalate crystals in moon rocks have been sitting there unchanged for billions of years. The moon has no atmosphere and no geological activity, so the crystals remain exactly as they formed. They are a frozen record of conditions in the early solar system. As you close your eyes and relax, think of those rare green escalate crystals sitting in moon rocks, some of them still on the moon's surface, others brought back to Earth where scientists can study these messengers from another world. Fact 33. Pyrrhotite crystals in meteorites. Pyrrhotite is an iron sulfide mineral that forms crystals in many types of meteorites. Unlike its cousin mineral pyrite, which is iron sulfide with a fixed ratio of iron to sulfur, pyrrhotite has a variable composition. It can have slightly more or less sulfur, which affects its properties. Pyrrhotite is interesting because it is magnetic, unlike most sulfide minerals. This makes it easy to identify and study. The pyrrhotite crystals in meteorites formed in the early solar system when iron and sulfur combined. These crystals are usually bronze or brown in color and have a metallic luster. When light reflects off a freshly broken surface containing pyrrhotite, the crystals shine and sparkle. The magnetic properties of pyrrhotite make it useful for studying the history of meteorites. Magnetic minerals can record the magnetic fields they were exposed to when they formed. By studying the magnetism preserved in pyrrhotite crystals, scientists can learn about magnetic fields that existed in the early solar system. Pyrrhotite is also found on Earth, often in igneous rocks that cooled from molten magma. The mineral forms at high temperatures, so its presence indicates that rocks were once very hot. In meteorites, pyrrhotite tells us that the parent asteroid was heated, either by radioactive decay or by collisions with other asteroids. Some pyrrhotite crystals in meteorites show interesting textures and patterns. The crystals may be intergrown with other minerals, or they may show signs of having been partially melted and then recrystallized. Each of these features tells part of the story of what happened to the meteorite's parent asteroid during its long history. As you settle down for sleep, imagine those bronze pyrrhotite crystals in ancient meteorites, their magnetic fields still preserving memories of the magnetic environment of the early solar system. Tiny archives of ancient cosmic conditions. Fact 34. Niningorite crystals in unusual meteorites. Niningorite is a rare magnesium sulfide mineral, found only in certain unusual meteorites. It was named after Harvey Nininger, a famous meteorite collector and researcher. Niningorite forms only under very specific conditions, low oxygen and high temperature. This makes it rare both on Earth and in meteorites. The meteorites that contain niningorite are called enstatite chondrites, the same type we discussed earlier. These meteorites formed in a region of the early solar system where oxygen was scarce. In this environment, magnesium combined with sulfur instead of oxygen, creating niningorite instead of the more common magnesium silicate minerals. Niningorite crystals are small and pale yellow or colorless. They are soft and fragile compared to most minerals, so they are easily damaged. When scientists study meteorites containing niningorite, they must be very careful not to alter or destroy these delicate crystals. The presence of niningorite in a meteorite tells us about the oxygen-poor environment where it formed. By studying niningorite and other unusual minerals, scientists can map out different regions of the early solar system. Each region had different conditions, and different minerals formed in each region. This helps us understand how the solar system was organized and how it evolved over time. Niningorite is one of the rarest minerals in the universe. It exists in only a small fraction of meteorites, and it has never been found naturally on Earth. Each crystal is precious to science because it provides unique information about a specific environment in the early solar system, an environment that may no longer exist anywhere. As you drift towards sleep, think of those rare, delicate niningorite crystals, formed in unusual conditions billions of years ago, preserved in meteorites, waiting for scientists to discover them and learn their secrets. Fact 35. Cristobalite crystals in lunar samples. Cristobalite is a high-temperature form of silicon dioxide, the same chemical compound as quartz, but with a different crystal structure. It forms when silica-rich material is heated to very high temperatures and then cools quickly. Scientists found cristobalite crystals in the lunar samples brought back by Apollo astronauts, evidence of the intense heating events that have affected the moon's surface. The cristobalite crystals on the moon formed during volcanic eruptions and meteorite impacts. When a meteorite slams into the moon at high speed, the impact creates tremendous heat. Rocks melt instantly, and silica in those rocks vaporizes. As the vapor cools, it condenses into tiny cristobalite crystals. These crystals then settle onto the moon's surface as part of the debris from the impact. The presence of cristobalite in lunar soil tells us about the violence of impacts on the moon. Every meteorite strike creates a flash of intense heat, briefly creating conditions where this high-temperature mineral can form. Over billions of years, countless impacts have sprinkled cristobalite crystals across the lunar surface. Cristobalite crystals are also found in volcanic rocks on the moon. During the moon's early history, volcanic eruptions brought molten rock to the surface. This lava flowed across the lunar plains, creating the dark areas we can see from Earth. As the lava cooled, cristobalite crystallized in some areas, especially where cooling was rapid. These volcanic cristobalite crystals are mixed in with other minerals in the solidified lava flows. The Moon's surface is a museum of impact and volcanic history, and cristobalite crystals are part of that preserved record. They sit unchanged on the airless Moon, waiting. Some have been collected and brought to Earth for study, while countless others remain on the lunar surface. As you relax into sleep, picture those tiny cristobalite crystals on the Moon, formed in moments of violence, now resting peacefully in the lunar dust. Fact 36. Augite crystals in basalt from Mars. Mars has sent us meteorites, rocks blasted off the Martian surface by asteroid impacts and eventually falling to Earth. Among these Martian meteorites, scientists have found crystals of augite, a common mineral in basaltic rocks. Augite is a pyroxene mineral, dark green to black in color, and it forms when basaltic lava cools. Finding augite in Martian meteorites tells us that Mars, like Earth, has volcanic basalt on its surface. The augite crystals in Martian meteorites formed when lava erupted from Martian volcanoes. Billions of years ago, Mars was once volcanically active, with enormous volcanoes much larger than any on Earth. The largest, Olympus Mons, is the biggest volcano in the solar system. These volcanoes erupted basaltic lava that flowed across the Martian surface, creating vast plains. As the lava cooled, minerals like augite crystallized within it. Studying augite crystals from Mars helps scientists understand Martian geology. The composition of the crystals tells us about the chemistry of Mars' interior. The size and shape of the crystals tell us how fast the lava cooled. Small crystals indicate rapid cooling, while larger crystals suggest slower cooling. By examining these details, scientists can reconstruct a history of volcanic activity on Mars. The augite crystals also contain trapped gases from the Martian atmosphere. When lava erupts, it can trap bubbles of gas. As the lava solidifies, these bubbles become trapped further in the rock. Scientists can extract and analyze these gases, comparing them to measurements taken by rovers on Mars. This confirms that the meteorites really are from Mars and not from some other source. As you prepare for sleep, imagine those augite crystals forming in Martian lava flows billions of years ago, witnessing the volcanic activity on ancient Mars, then being blasted into space and eventually falling to Earth where we can study them. Fact 37. Moissanite crystals in meteorites. Moissanite is silicon carbide, a crystal so hard that it is used as an alternative to diamond in jewelry. Natural moissanite is extremely rare on Earth, but it has been found in meteorites, where it formed in the carbon-rich atmospheres of certain stars. Moissanite crystals are messengers from distant stellar environments, places where silicon and carbon were abundant. The moissanite crystals in meteorites are tiny, often much smaller than a grain of sand, but despite their small size, they are remarkable. Each crystal formed in the envelope of a carbon-rich star, condensing from hot gas as the star shed its outer layers. These crystals then drifted through space for millions or billions of years, before being incorporated into asteroids, and eventually reaching Earth in meteorites. Moissanite is harder than corundum, and almost as hard as diamond. This extreme hardness makes the crystals very resistant to damage. They survive the journey through space unchanged, preserving information about the star where they formed. Scientists can analyze the isotopes in moissanite crystals to learn about nuclear reactions in stars. The discovery of moissanite in meteorites showed scientists that silicon carbide is a significant component of interstellar dust. Before this discovery, scientists thought interstellar dust was mostly made of silicate minerals and carbon. Now we know that silicon carbide crystals are common in space, especially around carbon-rich stars. These crystals play a role in the chemistry of the interstellar medium, and in the formation of new stars and planets. As you drift into sleep, think of those tiny, incredibly hard moissanite crystals, born in the atmosphere of a dying star, traveling across the galaxy. surviving billions of years, finally arriving here where we can admire their beauty and learn from them. Fact 38. Anorthite crystals in lunar highlands. The bright, heavily cratered highlands of the Moon are made largely of a rock called anorthosite, which is mostly composed of a mineral called anorthite. Anorthite is a calcium-rich feldspar, a light-colored crystal that formed when the Moon's early magma ocean cooled and crystallized. The anorthite crystals floated to the top of the magma ocean because they were less dense than the surrounding molten rock, creating a thick crust of anorthite-rich rock. This process happened about 4.4 billion years ago, shortly after the Moon formed. The Moon was completely molten at first, a globe of liquid rock. As it cooled, different minerals began to crystallize. Dense minerals like olivine sank toward the center, while light minerals like anorthite floated upward. Over millions of years, a thick crust of anorthite-rich rock formed, covering the Moon's surface. This ancient crust is what we see today as the lunar highlands. The anorthite crystals in lunar highland rocks are often large and well-formed. Because the magma ocean cooled slowly, the crystals had time to grow to significant sizes. Some anorthite crystals in moon rocks are several millimeters across, which is large for a crystal that formed 4.4 billion years ago, and has survived countless meteorite impacts since then. These anorthite crystals are among the oldest minerals we can hold and study. They crystallized when the solar system was still very young, less than 200 million years after the Sun formed. They have witnessed the entire history of the Moon and Earth. Every major impact, every volcanic eruption, every change in the Earth-Moon system happened after these crystals formed. As you close your eyes tonight, think of those ancient anorthite crystals in the lunar highlands, glowing softly in Earthlight, silent witnesses to billions of years of history. Some of the oldest crystals we know. Fact 39. Rutile crystals in shocked meteorites. Rutile is a titanium dioxide mineral that forms distinctive needle-like crystals. It is common on Earth, often found as inclusions in other minerals, and it's also found in meteorites. But some meteorites contain a special type of rutile that formed during high-speed impacts, when asteroids collide at tens of thousands of miles per hour. The impact creates a shock wave that briefly produces extreme temperatures and pressures. This shock can transform minerals, creating new crystal structures. One result of shock is the formation of tiny rutile needles that grow in specific orientations, creating beautiful microscopic patterns. These shock-formed rutile crystals are evidence of violent events in the asteroid belt. By studying their patterns and characteristics, scientists can estimate the pressure and temperature of the impact that created them. Some shock-formed rutile indicates pressures of hundreds of thousands of atmospheres and temperatures of thousands of degrees, conditions that lasted only microseconds but were intense enough to restructure minerals. The rutile needles in shocked meteorites are incredibly tiny, visible only under high magnification, but they are precisely organized, all aligned in the same directions, creating a regular pattern throughout the rock. This organization happens because the rutile forms along specific crystal planes in the original mineral, following the atomic structure even as it transforms. These rutile crystals tell the violent history of the asteroid belt, where collisions have been common for billions of years. Each impact creates fragments that may eventually fall to Earth as meteorites, carrying shock-formed rutile and other features that record the intensity of the collision. As you relax and breathe slowly, imagine those tiny rutile needles forming in a fraction of a second during an asteroid impact, their precise alignment preserving a moment of violence, now frozen forever in the meteorite. Fact 40. Hibonite crystals from early solar system. Hibonite is a rare aluminum oxide mineral that was one of the first minerals to condense from the hot gas of the solar nebula. These crystals formed when the solar system was brand new, when the sun had just ignited and the surrounding cloud of gas and dust was still very hot. Hibonite can form at temperatures above 2,500 degrees Fahrenheit, making it one of the earliest minerals to appear. The hibonite crystals in meteorites are tiny and dark blue or brown. They are found in the most primitive meteorites, those that have changed least since the solar system formed. These crystals condense directly from gas, floating freely in space before being incorporated into larger bodies. Each crystal is a time capsule from the very beginning of our solar system. Scientists study hibonite crystals because they contain unusual isotope ratios. These isotopes are different from what we find in most solar system material, suggesting that some hibonite grains are actually prasolar, formed before the Sun existed. These prasolar hibonite crystals came from other stars and got mixed into the cloud that formed our solar system. By analyzing the isotopes, scientists can learn about the stars that contributed material to our solar nebula. Hibonite crystals are so small that thousands of them would fit on the head of a pin. But despite their tiny size, they carry profound information. They tell us about temperatures and conditions at the birth of the solar system. They connect us to other stars that died and enrich space with new elements. They remind us that our solar system was not created from nothing but assembled from material that had a long history before the Sun even existed. As you settle into sleep tonight, think of those tiny hibonite crystals, some of the first solids to exist in our solar system, witnesses to its birth, carriers of stardust from ancient stars.